I want to take a moment to sort of talk about this model of computation that we are using over here. Okay, we are essentially using something that is based on a model of computation that's called the Kahn process network or the KPN model, right, named after the person who originally proposed it, right. The idea behind Kahn process networks is at its core very simple. All that it says is, supposing there are two computational elements A and B, and whatever is generated as output by A is then going to be consumed by B. We assume that they are going to communicate through something called a FIFO channel. Okay, a FIFO is essentially a first in, first out buffer. Okay, and implementing FIFOs, there are multiple ways of doing it. You can sort of imagine what is happening over here. If you want a first in, first out buffer, essentially all that you are saying is the first data that I put into this buffer should also be the first data that the other side is going to read out. Okay, in terms of data structures, right, what's the name that you would give for something like this? It's a queue, right? It's a first in, first out queue. Okay, in data structures there is also another alternative which is called the last in, first out. What is that called? A stack. Okay, so in this case we are not going to talk about stacks at all, because in terms of hardware especially, stacks are, at least they don't fit within this model of computation that we are trying to use. Okay, the first in, first out buffer on the other hand is perfect. It fits exactly with the notion of what we mean when we are talking about a signal processing algorithm, right? We have a certain signal which is coming in from somewhere. I need to perform certain operations on it, do some computations with it, and then forward it somewhere else for further computation. Okay, this is sometimes also called a streaming model. Right, or sometimes called computation with streams, right. So what we are sort of saying, the word intuitively, what you can assume when you hear the word stream is there is a continuous flow of certain kinds of information which is going from the input to the output. Okay, so in this case right now, if I have just two computational elements A and B, the assumption is that they communicate by means of this FIFO buffer. Okay, anytime that A computes something, it generates an output and puts it into that FIFO buffer, and B can then read from it and do something with it. Okay, which fits exactly with our notion of tokens in the data flow graph. Okay, so in the data flow graph I was marking those D's on the edges and saying, okay, these are tokens. How would you implement it exactly in terms of communicating FIFO buffers? Okay, so now you can sort of understand what that edge over there means. When I sort of say that there is an edge from, M to A, right, or rather from A to M and then another edge from M to A, what it means is there is a FIFO buffer between that adder and the multiplier, right, and that FIFO buffer, how big is it, how many data elements can it contain, we don't know yet, but it should contain at least one. I mean, it can store at least one data element. Okay, and what happens is the multiplier therefore just has to look at the FIFO buffer. Is something present over there? If it is, it can pull that out, multiply it and write that into its output FIFO buffer. Okay, so keep in mind over here that if I, for example, have something of this sort, I need to have at least one delay element over there, one token, but the FIFOs themselves, I could have FIFOs on both edges, right? That's just an implementation issue. The important point to keep in mind is, just because I have drawn two FIFOs over here, one on each edge, doesn't necessarily mean that there is actually data sitting in any of them. Okay, or in other words, one of them will always be empty, right, and the reason we are saying one of them will always be empty is because there is only one token delay through this entire loop, right. When I go from A to B and back to A, there is only one token delay, so at any given point in time only one initial condition to work with. Either A is ready or B is ready, both cannot be ready at the same time, even though I have drawn FIFOs over there. They don't have any data in them, the FIFO can be empty. Okay. So with that in mind, we can then sort of expand this out still further and say the Kahn process network is a very general model of computation, right? I can even have something of this sort. I can have something which says there is some A over here, another B over here, and both of them feed into C, which needs to do certain computation. Okay. So the simple model of it is of course very easy to understand. I can just say I have FIFOs over here. But the interesting thing becomes when I can further associate a number with each of these edges, right? So let's say I have 1 over here and 2 over here. What does that number mean? It means that for C to execute, it needs to wait until there is at least one data present on A and at least 2 data values present on the B edge, B to C edge. Okay. So with this model, essentially what I am saying is, every time C executes, it consumes one token from A and 2 from B on each execution, on each firing. Okay. And interestingly, I could also have that the output of C, I could associate some other number with it. Let's say that I put the number 4. Okay. In which case it produces 4 tokens on its output. Okay. This is valid. I am not saying that this is always to be done or anything of the sort, but having a token, having a functional node C of this sort is perfectly valid. It is possible. I can model it using this framework, right? Which means that I can then also create more complex networks over here. I can have something which looks like there is an A, it feeds into B, it also feeds into something else C, C in turn feeds into D, both of them then combine back into E and so on. Okay. Having a network of this sort is also possible, because at the end of the day all that I care about is there should be appropriate FIFO buffers everywhere. Right. Now the interesting thing about this model is that it allows you to sort of do certain kinds of analysis on the system, right? What kind of analysis? One of the main things that we would like to know in such a system is what should the sizes of those FIFO buffers be so that I don't run into problems, right? So an example of what kind of analysis you could do would be, how big should the FIFOs, how big or deep should the FIFOs be to avoid any kind of, what's the problem that happens when a FIFO fills up and you still try writing to it? It's called overflow. Okay. So overflow is one problem. Deadlock is another problem. Is it possible for a particular network to deadlock? Okay. These kind of questions within certain limited conditions can be answered using this model of Kahn process networks. Okay, not in general. In general, the answer to the question of is a Kahn process network ever going to deadlock, is the FIFO going to overflow, there it may be possible to construct certain things in which you can't really answer that easily, right? But by putting some additional constraints on it, you can actually answer those questions. There are problems with that, which is that the moment you start putting those additional constraints so that you can then answer the questions, is the FIFO ever going to overflow, will it ever deadlock, that also reduces the computational power of the system, right? One way you can think about it is, One problem that you might have noticed already with these Khan process networks, this kind of behavior is, how would you model conditional behavior, right? If I wanted to say, okay, if some condition is satisfied, do this, okay? The KPN model by itself allows that, but the moment you bring in that kind of a conditional node, you can no longer say anything about FIFOs, because now it basically says, okay, a token may or may not arrive at a particular buffer, okay? So the network model itself is very general, but what kind of analysis you can do and how you can sort of say whether or not it is going to work perfectly for your requirements usually requires you to put additional constraints on what can be modeled with it, okay? Alright, so let us just take a quick example to sort of get an idea of what we mean by this, right? In fact, this example that we talked about over here itself is a good one, right? I can straight away say that max size of F1 and F2 required. What is the maximum required size? How much is it? 1 token storage, right? Because there is only one D element over here, one initial token, right? So at any given point in time, I can either have one element on the FIFO between A to B or from B to A, not more than that. So either one of those FIFOs, just one is sufficient, okay? But what about this? What should the max FIFO size on this link be? There is no bound, okay? There is no fundamental bound from the theory itself, okay? So effectively, in other words, what it's saying is, because there is no dependency as such on A, it is capable of generating outputs as and when required, but if I don't put some kind of a physical limitation on how much data it can store, then I am most likely going to run into problems by having a FIFO overflow at some point, okay? So this is an example where the data flow graph or the network by itself does not impose a limitation on the size of the FIFO, or at least does not tell you anything about what should be the maximum size, okay? It does not bound the size of the FIFO, right? One thing that you may sort of recognize by looking from whatever we have seen so far is, in general, it is safe to put larger and larger FIFOs. You are not going to run into problems. But why would you not want to do that? Hardware, right? Basically, each FIFO involves some amount of hardware. Either it requires some memory for storing data, or it requires physical registers, shift registers, etc., which are also occupying space, right? So usually the question that we are interested in answering is, what is the minimum size that I can get away with, which will never lead to problems, okay? Let's look at another similar scenario over here, just to sort of understand the nature of FIFOs. Supposing I have a network that looks like this, right? And I have 2 and 1 over here, right? So what are those 2 and 1? Essentially saying that every time that A fires, it produces 2 tokens, and every time that B fires, it consumes 1 token, okay? Is this valid? Is this even acceptable? What would you say? Is such a scenario possible? Is it possible to implement something of this sort? Yeah, there is actually nothing preventing you from doing it, right? All that it means is, A will produce tokens at a certain rate, B is consuming only at half that rate, which effectively means that every time that A fires, B will have to fire twice to take out the data that A generated, okay? But that's all there is to it, right? One way of thinking about this might be, I have one simple way of looking at this would be, I have a sort of parallel to serial converter, right? Something which gives me 8 bits at a time, and the output I want to generate as 1 bit serial data, Okay, so a parallel to serial converter is exactly doing something of this sort. Every time that it fires, it generates a whole lot of data, which then has to be consumed by sort of 8 firings of that parallel to serial converter. Okay, what it means is that the firing rate or operating frequency or something, operating frequency is not exactly the right term, firing rate is actually the better way of understanding it, but one way you can think about it is that the rate at which the operating frequency at which the other node B is operating has to be higher than what A is operating at. Okay, so this kind of a system is usually called a multi-rate system. Okay, so a multi-rate system, this example that I have drawn over here just tells you why it is called multi-rate, because the rate at which B fires has to be higher than the rate at which A fires. Can they use the same clock frequency? Probably yes, because keep in mind that the clock frequency at which a system operates is different from the rate at which the sample frequency, or in other words the rate at which it pulls samples out of the system. Okay, so all that I am talking about here is the rate at which it is processing samples. I do not care about the internal clock frequency at which it is going to operate. Okay, now let us draw another variant of this graph. But now with feedback. Okay, and okay, what would you say is going to happen in this data flow graph? Let's sort of understand this a little bit better in terms of how it's, I'll just redraw it quickly over here so that we can look at the firing sequences. Okay, and I have two FIFO buffers sitting over here. Okay, initially how many data are sitting in this FIFO? 0 and 1. Okay, let's say that I fire this graph once. Okay, what does that actually mean? It means basically that I look at all the nodes that are sitting over there, I find out which one is ready and execute it. Okay. So right now in the original state A is ready to execute because it has one token sitting on its input, and according to that blue number written below A, it means that it requires one token on input in order to execute. What happens when it executes? It consumes that one token and generates two outputs. Okay. So I have two tokens sitting on that output FIFO and 0 sitting over here. Okay. Now what happens the next time? Now two tokens are sitting on the A to B edge. B consumes one token every time that it fires, therefore in principle it can now execute twice. Okay, so let's just go ahead and execute both of them. This comes down to 0, this goes to 4. Okay. So now 4 tokens are sitting on the B to A FIFO, which means A can now execute 4 times. Okay. So you see where the problem is. Essentially what ended up happening was this sequence of this sort of set of values for the production consumption parameters is unstable. Okay. So the FIFO will eventually overflow, no matter how big you make it, right? No matter how big you make the FIFOs between AB and BA, at some point if I carry on like this, they will end up overflowing. So even if I say, okay, I'm not going to execute both the B's at one time, it doesn't matter, there's still one token sitting on the A to B edge. If I carry this on for a little while, eventually I will definitely hit a point where both those FIFOs are growing without bound. Okay. So I will never be able to sort of keep this under control. In other words, this particular, all that it's saying is this is one possible KPN, right, a Khan process network, but is invalid for the reason that it can essentially result in unbounded growth in the FIFO sizes.